Welcome to Thought Frontier.
All right, everyone, get ready for today's deep dive. We're taking a close look at fusion power, that almost mythical source of clean energy that's been making headlines.
It seems like it's always just over the horizon.
Right, like, will it finally happen this time? So we've got 2 articles on the latest research and a YouTube video that's all about the investment and the momentum building in the field.
Yeah, there's a lot going on right now.
Definitely feels like a turning point, so we're going to break it all down. By the time we're done, you'll be totally up to speed on fusion power.
You'll be the fusion guru at your next dinner party.
Exactly. Okay, so first things first, for anyone who needs a refresher, what exactly is fusion power? It's not like splitting atoms like in those nuclear plants we have now, is it?
Nope, it's actually the opposite.
Opposite. Okay, tell me more.
It's like, imagine taking the tiniest atomic nuclei, like the ones from isotopes of hydrogen, and then you smash them together.
Smash them together.
Yeah, so hard that they fuse into a heavier nucleus, like helium.
Okay, I'm kind of seeing it.
And when that happens, a teeny tiny bit of mass is converted into a massive amount of energy. So basically, we're trying to recreate the power of the sun, but here on Earth.
Wow, that is ambitious. But if it works, I mean, the payoff is huge, right? No radioactive waste, no greenhouse gases, and a fuel source we can basically just get from the ocean.
Exactly. Deuterium from seawater, lithium from the Earth's crust. We're talking about a practically limitless supply of fuel.
It sounds too good to be true, honestly. But there must be a reason we're not all driving fusion-powered cars already. So what's holding us back? What are the biggest challenges the researchers are facing?
Well, the main challenge is heat.
Heat?
To get those atomic nuclei to fuse, we need to get to crazy temperatures, over 100 million degrees Celsius.
100 million?
Yeah, that's even hotter than the core of the sun.
Whoa, okay, so it's hot, but why?
At those temperatures, the fuel becomes a plasma, which is a totally different state of matter. It's where the electrons get stripped from the atoms.
Okay, so it's not solid, liquid, or gas anymore.
Exactly. It's this wild, supercharged state.
So it's got to be a plasma for this whole thing to work.
It is. Because, you see, those atomic nuclei are all positively charged.
Right, like tiny magnets, I remember.
Exactly. And just like magnets with the same poles, they repel each other. So we need to get rid of those electrons to get the nuclei close enough to actually fuse.
So the plasma is kind of like a cosmic dance floor where they can finally get close enough to, well, fuse?
I like that. But here's the thing. We've got to contain this superheated plasma somehow. We can't let it touch the walls of the reactor.
Why not?
Because it'll cool down instantly, which stops the whole fusion process. And it could also seriously damage the reactor.
So we need, like, a container that can withstand temperatures hotter than the sun. That sounds impossible.
It's definitely a challenge.
Yeah.
And that's exactly why we haven't got commercially viable fusion power yet. These 2 challenges, creating the plasma and then containing it, they're the big hurdles.
Gotcha. So what are scientists doing to tackle these hurdles? Are there any promising approaches out there?
Oh, absolutely. There are 2 main paths researchers are exploring: magnetic confinement fusion, or MCF, and inertial confinement fusion, or ICF.
Okay, let's break those down. First up, MCF, magnetic confinement fusion. What's the idea there?
So picture this. You've got this donut-shaped reactor called a tokamak.
A tokamak.
Yeah, and powerful magnets surround it, creating an invisible force field.
Like a sci-fi force field.
Pretty much.
Yeah.
And that force field keeps the superheated plasma suspended right in the center of the reactor, away from the walls.
So it's like a magnetic bottle holding a tiny star.
Exactly. We also have another type of MCF reactor called a stellarator.
Okay, another sci-fi name.
It uses even more complex magnetic fields, but it could be more stable for longer-term operation.
Interesting. And what about ICF, the other approach, inertial confinement fusion? That sounds a lot more action-packed.
It definitely is. So instead of using magnets to confine the plasma for a long time, ICF uses powerful lasers, or particle beams.
Lasers? Like a laser show?
Well, kind of. These lasers blast a tiny pellet of fuel from all sides, compressing it so quickly it heats up to fusion conditions in a fraction of a second.
So it's like we're using brute force to make fusion happen in a blink of an eye.
You got it. It's
Yeah.
a totally different way of achieving the same goal.
Awesome. So we've got these 2 main approaches, MCF and ICF. Are there any recent breakthroughs that have scientists excited?
Oh, definitely. Over in the UK, the tokamak, that's Joint European Torus,
Catchy.
they just hit a major milestone, generating a record 59 megajoules of energy from fusion for a full 5 seconds.
5 seconds. Is that a lot?
It is. It might not sound like much, but it proves that we're on the right track.
In what way?
Because it validates the design and operation of ITER,
Hmm.
which is this massive international project.
Sure.
Yeah, it stands for International Thermonuclear Experimental Reactor.
Okay, that one's a mouthful.
It's a huge endeavor aiming to show that fusion power is actually feasible on a large scale. So think of G as like the successful test run before the main event.
Gotcha. So jet is a good sign for ITER.
Absolutely. And on the other side of the Atlantic, we've got the National Ignition Facility, or NIF, which is making progress with their fast ignition technique.
Fast ignition.
Yeah, it's aimed at achieving fusion at lower temperatures, which could make the whole process way more efficient and practical.
Lower temperatures, easier to achieve. That makes sense.
Right. And then there's the East Tokamak in China.
Easy.
It stands for Experimental Advanced Superconducting Tokamak. They just set a new world record, maintaining a plasma temperature of 120 million degrees Celsius for 101 seconds.
That's hotter than the sun for over a minute.
It is. They even hit a scorching 160 million degrees Celsius for a shorter time.
Wow. It seems like the global fusion race is really heating up.
Pun intended.
Maybe. But it's not just governments involved anymore, is it? We've got all these private companies jumping into the ring too, right?
You're absolutely right. And they're bringing a whole new level of energy and innovation to the game. These companies are like the startups of the fusion world.
That's a great way to put it. So I'm definitely curious to hear more about what these companies are up to.
Yeah, let's dive into that next.
Awesome. We'll be back after a quick break to explore the world of private fusion ventures. Stay tuned.
Welcome back. We're in the middle of our deep dive into fusion power, and last we left off, we were talking about these private companies jumping into the game.
Yeah, it's like a whole new frontier in the fusion world. We've got these established labs doing their thing, and then suddenly, bam, all these startups enter the scene.
It's pretty exciting. They're bringing a fresh perspective, tons of energy.
And money, right? I mean, they're attracting serious investment.
Absolutely. Hundreds of millions, even billions of dollars are flowing into this field.
Wow. So it's not just about science anymore. It's about business, making fusion commercially viable.
Exactly. They're laser focused on turning this dream into a reality.
Okay, so who are these fusion entrepreneurs? Give me the rundown of the ones to watch.
Well, we already mentioned tokamak energy a bit earlier. They're all about those spherical tokamaks, which is a smaller, more compact design.
The squished donut, right, I remember.
That's the one. They're really betting big on high-temperature superconducting magnets, too.
Those magnets are key to making the reactors more powerful, right?
Exactly. And smaller, too. Traditional superconducting magnets have to be kept super cold, which requires a lot of energy and bulky equipment.
Yeah, those giant freezers are not exactly practical for a power plant.
Right. But these high-temperature magnets can operate at, well, higher temperatures. Makes them way more practical for a fusion power plant.
It's like they're supercharging their magnets without the need for a giant icebox. And they're aiming to have a prototype connected to the grid by 2030. That's only a few years away.
It's ambitious for sure.
Yeah.
But they're not the only ones moving fast. We've also got General Fusion up in Canada.
Oh, yeah. Those are the ones with the steampunk octopus, right? I love that description.
It's pretty accurate. They're using magnetized target fusion.
Remind me how that works again.
So imagine a sphere, right, filled with molten lead and lithium all swirling around.
Molten metal. That sounds dangerous.
Well, contained, of course. It's like a liquid tornado.
Okay, I'm picturing it.
And in the center of this vortex, you have a little pocket of plasma.
The plasma with the fusion fuel.
Exactly. And then, get this, they use a bunch of pistons to compress that liquid metal all at once.
Pistons, like in a car engine.
Kind of, but way more powerful.
Okay, so they're squeezing the plasma with these giant pistons.
Exactly, and that creates the conditions for fusion.
So it's like they're creating a mini sun by crushing it with a giant robot octopus.
You got it. Definitely a creative approach.
And I hear they have some big-name investors, too.
Oh, yeah. Jeff Bezos is on board, among others. They're planning to build a demonstration plant in the UK by 2026, so things are moving quickly.
2026? Wow, that's coming up fast.
Yep.
Okay, who else is on our list of fusion all-stars?
Well, we can't forget about Helion Energy down in the U.S. They've raised over $500 million.
$500 million. Someone must believe in them.
For sure. They're the ones with the field-reversed configuration approach.
Field reverse what now?
It's basically a self-stabilizing ring of plasma held together by magnetic fields.
Okay, I'm vaguely following.
But what's really cool is their focus on direct energy conversion.
Right, they skip the whole heat-to-steam process and generate electricity directly from the plasma.
That's it. Super efficient, potentially game-changing.
Makes sense why investors are throwing money at them.
All right, last but not least, we've got First Light Fusion over in the UK.
Ah, yes, the projectile fusion, folks. That sounds kind of wild.
It is. Imagine a powerful gas gun.
Okay, a gun.
Yeah, but not a regular gun. This thing fires a projectile at insanely high speeds.
A projectile? Like what kind of projectile?
Doesn't really matter. Anything dense will do. The point is, it slams into a target that has the fusion fuel in it.
So it's like a super high-speed collision.
Exactly. That impact creates an implosion, which generates the insane temperatures and pressures needed for fusion.
So they're basically playing a high-stakes game of atomic billiards.
Pretty much. And the crazy part is, it actually works. They've already demonstrated fusion using this method.
Wow, that's incredible. It's amazing to see all these different approaches, like everyone's trying to crack the fusion code in their own way.
It really is. It's like the fusion field is having a renaissance, all these new ideas bubbling up.
I love it. But let's step back for a second. Even if one of these companies figures out how to get net energy from fusion.
Which is a big if, of course.
Right. But even if they do, there's still a long road ahead before we have fusion power plants popping up everywhere, right?
Oh, absolutely. Scaling up from a lab experiment to a full-blown power plant is no easy feat.
There must be tons of engineering challenges to overcome.
Oh, definitely. For one thing, material science is a huge hurdle.
Materials? What do you mean?
Well, think about it. Inside a fusion reactor, you've got insane temperatures, radiation, these high-energy neutrons bombarding everything.
Right. That can't be good for anything.
It's brutal. We need materials that can withstand that kind of punishment for a long, long time.
So it's not just about making fusion work, it's about making it work reliably.
Exactly. And then there's a whole issue of tritium.
Tritium.
It's a radioactive isotope of hydrogen that's needed for a lot of these fusion reactions.
Okay, and that's a problem.
Well, we need to figure out how to produce and handle it safely and efficiently inside a power plant, because it's not exactly something we find just lying around.
Right, safety first. Any other hurdles we need to be thinking about?
Well, there's always the cost factor. Building and operating a fusion power plant is going to be expensive.
Makes sense.
So we need to make the tech more cost-effective or won't be able to compete with other energy sources.
Yeah, even if it's clean and sustainable, it has to make economic sense, too.
Absolutely. And then we have to think about grid integration. Our electricity grids are designed for these big centralized power plants.
So fusion might need a different approach.
It might. It could be more suited for smaller, decentralized setups.
So it's not just about building the tech, it's about rethinking our whole energy infrastructure.
Exactly. It's a complex puzzle with a lot of moving parts.
Well, I'm glad there are brilliant minds working on it. So we've talked about the benefits of fusion, the challenges, the exciting advancements, and the key players. But now I'm curious, what happens if we actually succeed?
What happens when fusion power becomes a reality? That's the million-dollar question.
What does that world look like? Is it all sunshine and rainbows, or are there potential downsides we haven't considered?
There are always things to consider. For example, one concern that often comes up is the misuse potential.
Misuse? How so? I thought fusion was supposed to be clean.
Well, the reactions themselves are relatively clean, but the process releases neutrons.
Neutrons, those are those subatomic particles, right?
Yeah, and they can make some of the reactor components radioactive.
Oh, so even though fusion is way cleaner than fission, it's not totally free of radioactive material.
That's right. And that raises some concerns about what could happen if those materials fell into the wrong hands.
Right, like could someone use fusion tech to build weapons?
It's a possibility we have to consider, unfortunately. And it's not just about weapons. It could also be used for, other harmful purposes.
So it's not just about making fusion power work, it's about making sure it's used responsibly.
Exactly. We need strong international regulations, safeguards, to prevent the spread of fusion tech that could be used for bad stuff. It's going to take a global effort.
A lot of responsibility comes with this kind of power, literally and figuratively. What other potential downsides are there?
Well, and another concern is energy equity. If fusion takes off, it could totally change the global energy landscape, shift the balance of power between nations.
So some countries might benefit more than others.
Exactly. We have to make sure the benefits of fusion are shared fairly, not concentrated in the hands of a powerful few.
It would be a shame if fusion just made the rich richer and left everyone else behind.
Definitely. We have to be mindful of that. And then there are the economic and social impacts to think about.
What do you mean?
Well, transitioning to a fusion-powered economy could be pretty disruptive.
Like people losing jobs in the fossil fuel industry.
That's one example. We need to figure out how to manage that transition smoothly, support workers who might be affected.
Makes sense. We can't just leave people behind in the rush to a new energy source. Are there any other unforeseen consequences we should be thinking about?
It's hard to predict everything, of course, But we need to consider the environmental impact, for example.
Like, what would happen if we built fusion power plants all over the place?
Could be unintended effects on ecosystems, wildlife, even climate patterns.
We have to be careful. Proceed with caution.
Absolutely. We need a healthy dose of humility, recognizing that we don't have all the answers.
It's a reminder that technology is powerful, but it's not a magic bullet.
It's a tool. And like any tool, it can be used for good or for bad.
We have to make sure we're using it wisely. This has been a really eye-opening conversation. It's clear that fusion power is about so much more than just science.
It's about society, ethics, the future of our planet.
It really makes you think about what kind of world we want to create.
We have the chance to build a better future with fusion, but it's up to us to make the right choices.
That's a powerful message. Well, deep divers, that brings us to the end of our fusion power deep dive. We've explored the science, the challenges, the potential benefits, and the ethical considerations.
It's been a fascinating journey.
I hope you all learned something new and feel a little bit more informed about this incredible technology.
Fusion power has the potential to transform our world, but it's important to remember that the future is not predetermined.
It's shaped by the decisions we make today.
So let's keep asking those tough questions, keep learning, and keep striving for a brighter, more sustainable future.
We'll be back soon with another deep dive into the world of science and technology. Until then, stay curious and thanks for listening.